While studying kinematics, we saw that we could use math to predict the motion of an object. We could figure out where it has been in the past, where it will be in the future, how long it took to get there, and even how fast it was traveling. What we were really doing was analyzing how an object was moving. But why was it moving in the first place? In other words, what is it that causes an object to speed up? The answer is surprisingly simple. The only thing that can cause an object to accelerate is a force. In this video, we'll look at how forces influence the motion of different objects, and we'll challenge our intuition of how things work in the physical world. Here is a wooden apple resting on a countertop. Before seeing anything else, you've probably made a number of assumptions. We rightly think that the marble counter is heavy and rough, and that the apple is smooth and light. Say we plan on giving the apple a shove to the right. We all have an idea of how the apple will slide and stop. And thanks to our intuition, we can make predictions like this on a moment-to-moment basis without much effort at all. But what if it were possible to remove everything that our intuition is based on? What if we could remove all the air in the room, which can cause air resistance? Remove all the friction from the ground and walls, and remove the force of gravity. Now if we pick the apple up and let it go, it won't move anywhere because there's absolutely no forces acting on it. If we bump the apple now, would it ever stop moving? The truth is, once we give the apple a bit of velocity, it stays at that velocity, moving in a straight line until it's bumped again. This isn't just an imaginary experiment. It turns out that this is exactly what happens in outer space. But before we go any further, let's look at a little history. The first person to make this claim lived over 300 years ago. His name was Sir Isaac Newton, and he was a brilliant scientist, brave enough to challenge our intuition about everyday physics. Newton's goal was to figure out how the world around him worked. He had the thought that everything we see follows a few simple rules, which when added together, build up to explain the complicated physical interactions all around us. Newton's predictions are now known worldwide as Newton's 3 laws of motion and are used when dealing with anything that moves, from cars and trains here on Earth to spaceships that fly to the moon. At the start of the video, we asked the question, what causes an object to speed up? Newton answers this question in his first law of motion. An object with constant position or constant velocity will remain at that position or velocity unless acted upon by a net external force. Well, this is just reiterating what we already realized. The only thing that could cause our apple to accelerate was a force. So what is the next logical step in understanding why things move? If we now know that a force causes acceleration, we might also wonder how much acceleration we can get from a certain force. The answer to this is actually Newton's second law of motion. F is equal to m multiplied by a. This means that if you want to speed up an object by a certain amount, you will have to adjust your force depending on the mass of the object. Heavier objects need stronger forces. Let's look at what this math means in real life. There are 3 variables in the equation, so we'll look at 3 examples, each with one variable held constant. But before we start, let's bring back gravity. Okay, first let's hold the mass constant. Let's bring in 2 toy blocks of the same size. This part is pretty intuitive. If we gently push the first block, it'll accelerate slowly. But if we push the second block with twice the force, it's going to accelerate twice as fast. What if we were trying to push something much heavier, like two large masses? Now our robotic arm has to push at 100% of its strength to move these objects. And when we push the heaviest mass, it's a big struggle. But when we push the smaller heavy mass, even though we're pushing with the same force, we can make it move faster because it's lighter. In our third experiment, let's drop a hammer and a feather from the same height at the same time. What does your intuition tell you will happen? Most people imagine the hammer hitting the ground first, because it's heavier, so it falls faster. Let's try it out. They hit the ground at the exact same time. Amazingly, humans have actually done this experiment on the moon, and it turns out that our predictions are completely correct. Let's look a bit more at this third experiment, since its results are a bit unexpected. If the acceleration of the hammer and feather are the same, then what does that tell us about the forces and masses? Well, we know that the hammer has more mass than the feather. So that means that for the math to work out, the force of gravity on the hammer must be more than the force on the feather. So we know from Newton's second law that the hammer and the feather fall at the same speed, because even though the hammer is pulled with more force, it also has a greater mass. So in the end, the ratio of force to mass is the same for the two objects. This is why they fall at the same rate. What we have just stumbled upon is actually a very important distinction in science. The force of gravity acting on an object is known as its weight, which is not the same thing as the object's mass. You can think of mass as something that belongs to an object no matter where it is, whereas the weight of an object changes depending on the gravity of the planet that you happen to be on. In outer space, your weight would be 0 newtons. But since acceleration is constant at 9.8 meters per second squared on Earth's surface, we can use the force of gravity is equal to the mass times the acceleration of gravity to quickly find the weight of an object from its mass, or vice versa. For example, the weight of a 10 kilogram mass on Earth's surface is 10 kilograms multiplied by 9.8 meters per second squared, or 98 newtons. So now let's look back and try to explain why our intuition was wrong. What goes on when there is air resistance that makes the feather fall more slowly? Let's look at the feather on its own to start. We just found out that the feather has a small weight because it has a small mass. So this means that the force of gravity pulling on the feather is relatively small. So let's draw a small arrow to represent the force of gravity acting on the feather. What other forces are acting on the feather? Well, in a vacuum, gravity would be the only one. But with air resistance, there is actually a second force acting on the feather, in the opposite direction to the force of gravity. For a hammer and a feather, the force of air resistance is nearly equal. But since a hammer has such a larger mass, the hammer barely notices this small force of air resistance. For most calculations in high school physics, we deal with objects that are large and fairly heavy, so you can usually ignore air resistance. But for a feather, it makes all the difference. The analysis technique that we have just used is one that you will use all the time from now on. The use of arrows to represent all the known forces acting on a single object is called a free body diagram. For problem solving in physics involving forces, you will almost always start by drawing one of these. On that note, we are now completely ready to tackle Newton's third and final law. So far we have answered our two biggest questions. First, what causes an object to accelerate? And second, by how much does the object accelerate given a certain force? It might seem like we have asked the two most important questions, but Newton thought of one more question to answer, which most people might not have thought of. The first two laws are centered on an object that is accelerated by a force. But what is providing the force in the first place? Newton's third law is that there is no such thing as a lone force. All forces come in pairs. In technical language, for every action force, there is an equal and opposite reaction force. Let's look at some examples. When a robotic arm pushed on those masses as hard as it could, the masses were actually pushing back on the robotic arm with the same force. When the Earth pulled on the hammer as it was falling to our studio floor, the hammer was actually pulling back equally hard on the Earth. But since the Earth is so large, we don't notice the Earth accelerating towards the hammer. And as you sit in your chair pushing it down with your weight, it pushes back on you with an equal force. You wouldn't even be able to walk if Newton's third law weren't true. When your shoes push back on the ground pushes forward on your shoes, and this is the only reason you are able to walk forward. Okay, let's take a breather. We've now covered all three laws of motion, and there were probably a few things we covered that didn't immediately make sense. Let's look at a generic example involving forces, and use Newton's laws along the way just to solidify our understanding of everything so far. Say we have an object of mass m. Let's draw a free body diagram of the four most common forces we can think of. The first force to think about is the one that is always there, no matter what, when your object is on Earth. The force of gravity. Again, thanks to Newton's second law, we know that this force is equal to mg. The second force to think about comes from this question. Is the object free falling, or is it resting on the ground? See, if the object is free falling, then there is only the force of gravity acting on the object, ignoring air resistance. If the object is on the ground, then we know from Newton's third law that there must be another force pushing up on the object. In other words, if our object is pushing down on the floor, then the floor must also be pushing up on the object. This upward force is known as the normal force, and is the reason why solid objects, like humans, don't fall through the floor. But what is the normal force equal to in this case? Well, we know that if our object isn't accelerating, then there is a total of zero force acting up or down. And this means that a normal force cancels out with the force of gravity, or Fn equals m multiplied by g. But what if someone applied a third force by pushing down on the object? Wouldn't they beat the normal force pushing up and make the object go through the surface? This is where the normal force cheats to make everything work out, so that what we see agrees with what we calculate. See, the normal force will always adjust so that it is exactly equal to the sum of all forces acting down on the object, but in the opposite direction. Alright, so what if we applied a small force to the right? We know that in real physical systems there will be some kind of frictional force counteracting our force to the right, so this is the fourth type of force. But how strong would the frictional force be? To answer this, we need to really understand what causes friction. Look at the surface that the mass is resting on. From far away, it looks like the surface is a pretty smooth line. But when you zoom in, you can begin to see little valleys and hills which come together to form the seemingly flat surface. These imperfections cause many miniature reaction forces acting backwards on the object, in response to its being pushed forward. When you add up all these tiny forces, you can find one overall force pushing back against you, and it is this force that we call friction. You should know that there are other types of friction, and that even this explanation is a simplification. But for now, this will help us understand what is to follow. Imagine that we start to push our object to the right. Just like the normal force, friction will at first adjust to counteract the force we are applying to the object. But unlike the normal force, if we push hard enough, we can beat friction. This initial friction that must be beat for an object to start moving is called static friction. And when we are pushing at just the right force, such that if we pushed any harder the object would start to slide, we know we are at the maximum force that static friction can provide. And it is this maximum force that is most useful for the math. We can solve for this maximum force of static friction with the equation Ff equals μs multiplied by Fn. And that's it! We know all about Fn, the normal force, and Fs is the maximum force of static friction. But what about the symbol in the middle? It's a Greek symbol called mu, and it represents the coefficient of static friction. This is a unitless constant that depends entirely on the two materials that are sliding past each other. For example, the rubber of your car tires on concrete has a coefficient of around 1, which is very high. An ice cube sliding over a sheet of ice has a coefficient of around 0.1, which is very low. So what happens when we push harder than the maximum force that static friction can return? It turns out that there's another type of friction that takes over once an object is moving. And you'll be happy to hear that it's a tiny bit simpler than static friction. Kinetic friction is what we call the force of friction acting on a sliding object, and its formula is Ff equals mu k multiplied by Fn. This formula looks almost the exact same as the one for static friction, but we've got to be careful. The static and kinetic frictional forces have a lot of differences. Let's look at another block being pushed to the right, but this time we'll analyze the motion in a little more detail. Here we have a graph of the force of friction on the left, and a graph of the force we are applying to the block on the right. So at first, static friction takes over and keeps the block from moving. As we increase our applied force, it responds accordingly. This continues until, snap, the maximum force of static friction has been reached and now kinetic friction takes over. There are two key points to realize here. First is that the kinetic friction is constant. It will never change no matter how fast the block is traveling. Second is that the force of kinetic friction is less than the maximum force of static friction. This is true for most materials that you'll be working with. Okay, we're almost done. Let's look at the two equations for friction and see if we can learn anything surprising. First, let's look at the normal force. We already saw that we could increase the normal force by pushing our object down against the ground. And it looks like, from the math, that increasing the normal force will increase the force of friction. This completely makes sense if you try it. If you push a block along a table and then have someone put their weight down on the block, it will be much harder to push along. Another observation we can make is that there is something missing in the equation that we might have expected to be in there. Doesn't the surface area of the touching materials matter for the frictional force? It turns out that the area of the contacting surfaces between two objects has no effect on the force of friction acting between them. This means that it wouldn't matter if you push the block on the wide side or the narrow side. The force of friction would remain unchanged. But why? Well, it actually has a lot to do with what we just learned about the normal force. Look at how the upright block has a smaller contact area, but since the block is vertical, there is more mass per unit area of contact. This means that there's more normal force per unit area, and we just learned that this increases friction. So the decrease caused by the surface area is exactly countered by the increase caused by the normal force per unit area. And with that, we've now covered the basic concepts involved with forces. In introductory physics courses, you'll likely have to solve different problems involving the four forces we've just looked at. If you understand all the properties of these four forces and have a good grasp on Newton's laws of motion, you will be able to tackle any question that comes your way.